Welcome everyone. Today we're going to talk about deadlocks, continuing what we started last session. Today's lecture is important, so again I would like to ask everyone to set aside their laptops and phones and pay more attention. Today's lecture include a couple of algorithms. Some of them have similarities, but you have to be able to differentiate when to use which. So let's get to it. So last session we talked about the deadlocks, the 4 conditions that should hold in order to have a deadlock state, and we learned what is a resource allocation graph, and also learned about the deadlock prevention, which was to prevent from one of the conditions for the deadlock to hold. And then we had the submission for design doc. A few of the students had some issues, which is again a little bit unfortunate. So hopefully we won't have any of such problems for next submissions, especially for your code submission, because it is a 90% of the grade. Make sure you stay on time. Submit your empty code several times beforehand, so there's no issue. Your groups, you have to create your groups on AutoGrader for all the design docs and every source code project, which is basically 6 times. We've covered only, we went over once. So for all the other ones, make sure you create your groups as TAs has suggested on the instructions on Piazza. Copy and paste your group name exactly as they are on the GitHub Classroom. And make sure you confirm your invitations. Then one more thing, I forgot. So next session, also next week on Tuesday, which is your midterm, there's also due date for your homework too. So basically after today, the lectures are over, so you can already I think answer either all of them, or at most after today you can hand over your homework to next session, so you don't have to actually wait for next Tuesday. But I will collect them on Thursday and next Tuesday. All right. So and make sure you commit. Oh, this is the other thing. So when I looked at the repos on GitHub, a lot of the groups are not making so many commits. That's not good. Either you're working on a local repo, or maybe you're working on a separate repo, or you're just not committing a lot, meaning you're just modifying, but not committing. That's not good, right? Every now and often, make sure you make a commit. Every now and often, push it so your repo stays up to date. Even if you're working together on a single laptop, so that you don't push and pull, but do it because you never know. You don't want to lose your code. So make sure you commit regularly. All right. So today we're going to cover the rest of the handling deadlocks. So first we're going to talk about avoidance, and then detection and recovery. So deadlock avoidance is a bit different than prevention. So we learned about deadlock prevention, and that is basically ensuring that one of the 4 necessary conditions for deadlock does not hold. And so the possible effect of that is basically a low device utilization and reduced system throughput. So avoidance, it means that we ask or basically expect the processes to give the system information ahead of time about their possible requests, so that later on the system can dynamically examine the request and then decide, is this request valid? Should it be granted or not? So for example, a process can again give ahead of time information to the system that I may request a disk and then a printer, whereas maybe another process may say, okay, I want a printer then disk. So in this case, then the system can see a possible possible deadlock state in the future. So dynamically, based on the order of request, it can decide, okay, maybe a process should wait so that we don't end up in a deadlock state. So, or for example, the other example is when we have multiple instances of a resource type. If processes tell the system that I may request, at most n of each resource type. Again, this is another method. So, and it allows for more concurrency because it is like, examined dynamically. Then, depending on the order of the request, maybe, there is no problem. So, they all run and then none of them has to wait. So this comparison is basically similar to the difference between a traffic light and a police officer, right? So when a police officer is there in the intersection, they have a bit of, of intelligence. They dynamically see the, throughput. There are so many cars on this side. They can, guide. And then at the same time, if there is another car that does not actually have to wait for these, that they're just turning left, they can guide them. It's a little bit more efficient than just like a traffic light. All right? So the simplest method is when we have, again, multiple instances of each resource type, the processes can basically declare that the maximum number of resources that they may request. All right? And the deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can be no deadlock. Right? Again, when they declare the maximum number, that doesn't mean that they're requesting, but it gives the system some insight to their future or possible requests. And so, if an allocation might end up in a circular wait, then the system can say, okay, you should wait for a bit so that, we avoid this. And something that we're going to talk about and use is a resource allocation state. So a resource allocation state is like a snapshot of the system and shows how many of each resource type has been allocated to each processes, right? And based on the number of they may request or they have declared, and based on the current state, the system can decide, all right? So we're going to see how this works. So a safe state is basically when a system can allocate resources to each processes up to its maximum in some order without any deadlock, not necessarily at the same time. So we are in a safe state if at the moment whatever the processes are there on the system and they have declared a maximum number of resources that they want, right? We are in a safe state if we can make sure that in some order they will run. They can they can request up to their maximum number of resources, and with no problem they can finish and terminate and without any deadlock. So when a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. So as long as you are in a safe state, you can grant resources to the processes. If this allocation, leaves the system is still in the safe state, that's fine. If it jeopardizes it, then the system might say, okay, you should wait because we are not in a deadlock now, but I'm just it's safer for you to wait so we don't end up in a circular wait. And then it's avoiding deadlock by making that process wait. All right? So, and a system is safe state if there is a safe sequence of all processes. Right? Let's see. So a sequence of different processes, P1, P2, all the way to the Pn, is a safe for each Pi if the resources that Pi can still request can be satisfied by currently available resources and resources held by all the Pjs smaller than Pi. And so let's take a look. So this P1 to Pn, they're not necessarily the PIDs, right? They're just like a sequence. So that means, let's say, the first P1, when we have some available resources, P1 should be able to, request their maximum resources, and we should have them available. So that's fine. That means P1, even if you have to make sure all the other processes wait, P1 can request its maximum resources because we have them available, and then it can run and then finish. What happens when the P1 finishes? What? It releases the resources that it has, right? And so then our available resources will be increased, right? Because some of them were held by P1, and now that when P1 is done, it will release its resources. Now we have more available resources that we can give to P2. So if now P2 requests can be satisfied with what we have available right now and the ones that are held by P1, which it may release, then P2 can start and finish. So when P2 finishes, it will release whatever that it has, held at the moment. And then our future available resources again will be increased. So when we're thinking about P3, if P3 requests can be satisfied by what we have right now and the resources held by P1 and P2, which can be, released in the future, then again P3 can be satisfied. The P3's request can be satisfied, and so on. And then this is the sequence. That's why it's a sequence. So one at a time, we can, at worst case, we can, make all the other processes wait, and one at a time let them finish. All right. So then all of them can finish, and then it's safe. So if PI resource needs are not immediately available, then PI can wait until all the PJs have finished, and then the available resources now go up. And then they will also obtain the needed resources, execute, and return allocated resources. And then the next process, right? So we're going to see it in a couple of examples, but, if it's not clear, you should ask and we come back to this slide, right? And if no such a sequence exists, then the state is not safe. If, among all the processes, we cannot come up with an order that, one at a time they can execute safely, then the system is unsafe. Does it mean that we have a deadlock? Not necessarily, right? So let's see. So let's think that we have processes 1 to 5, and then 3 resource types. We have 7 instances of A, 2 instances of B, and 6 instances of C. All right, listen carefully because you might just get lost because we're not doing it on the blackboard. So I should just keep adding up numbers, without writing them down. So at the moment, at this snapshot, remember we have 7, 2, and 6. At the moment, each process has been allocated these many resources, right? So we have 7 instances of A, 2 of them is to P2, 3 here, and 2 here. And that's all the 7. We have 2 instances of B, 1 is held by P1, 1 is held by P4. And we have 6 instances of resource C, 3, 1, 2, allocated by 3. So far clear how the allocation matrix is? And now, that's why we don't have anything available, because all of them are allocated. Now, the requests, and it's if these processes are requesting, or they may request these in future, is like this. So P1 does not request anything. P2 may request 2 of A and 2 of C. And then P3, again, nothing. P4, 1, 0, 0. P5. This is, again, either right now they're requesting or they may request in the future. Are we in a safe state? Yes. How? By showing a safe sequence. The safe sequence, that doesn't have to be unique. There should exist at least one safe sequence. So this sequence is safe because if you look at the order, P1, 3, 4, 2, 5, can be allocated their requests, safely finish, then release their allocated resources. Let's see. So for example, P1. P1 does not request anything, right? So we can let P1 finish without allocating anything, and when P1 finishes, it releases 1B. Now, then we can, again, this P3 doesn't request anything, so then it will run completely, finish, and then releases 3 of A and 3 of C. So by the time we are done by P1 and P3, we have 3, 1, 3 available. Then, using that 3, 1, 3 available, we may grant this request to P4, and then P4 finishes, and when P4 finishes, it will release whatever that it holds right now. 2 of this, 1 on this, and then 1. So then we will have 3, 1, 3, 5, 2, 4. When P1, 3, and 4 finishes, then we will have like 5, 2, and 4 resources. And with those, we can basically grant all of them. So, again, 2 or 5 or 2, it doesn't matter. So we can come up with this sequence so we are in a safe state. So if we are in a safe state, there is no deadlock, that's for sure. Because again, we can have that sequence, run it, and have all the processes finished. Some of them might have to wait, but there's no deadlock. If a system is in an unsafe state, that doesn't guarantee a deadlock, but there's a chance of a deadlock. It depends on the order of request. Maybe a processor may request its maximum number, but maybe it actually does not, right? We don't know. And so this is like, safe and unsafe and deadlock kind of diagram. And the deadlock avoidance algorithm that ensures that the system will never enter unsafe state. Initially, we are always in the enter the unsafe. Initially, we are always in the safest state, right? Initially, there's no problem. So dynamically, it always ensures that we don't leave the safest state and don't enter the unsafe, right? So another example here. So a system that has 3 processes, and we have like 12 disks, so just 1 resource type and 12 instances. So P1, P2, and P3 currently are holding 5, 2, and 2, and their maximum need is 10, 4, and 9. Are we in a safe state or not? Let's see. When we have 12 and the currently allocated is 9, that means we have 3 available, right? So with this 3 available, P2 may need 2 more. So we can grant P2 its available, resources, wait for P2 to finish, and then P2 will release this 2. Then we have 5 available. Now, with 5 available, P1 may need 5, right? It's holding 5. It may need, a total of 10, so it may need 5 more. And by the time P2 is finished, we have 5 available, so there's no problem. So P1 can, grant all those 5 and finish all the way, then release this 5. And then now we have 10 available, which then P3 can, take and then work with it and then finish. So currently we are in a safe state. Let's now have a request by P3. Remember, the sequence that we came up was P2, P1, P3. So if P3 requests the 3rd disk, should we grant it or not? Let's see. It seems fine because, if we have like 5 available, we had 3 available. If we grant 1 to P3, then we still have 2 left, right, that P2 can use. So there's no problem, right? No, because again, you have to look all the way ahead and see a possible deadlock. If we grant 1 more disk to P3, like this, then we'll have 2 available. This 2 can be used up by P2. But when P2 finishes, it will release only 2, right? That will give us a total of 4 available resources. But P1 may require 5. If we grant this one to this, and in the future P1 requests all 5, we won't have them. We only have like 4. And then we'll have a deadlock. So by the time that this request is made, the system should not allow this to happen and then wait for, P2 to finish. Yes?
When P2 finishes, why doesn't it release all 4?
Well, all 4, it will release whatever it has held. Right? If it has held 4, then it will release 4. Right now, it is holding 2. If it gets 2 more and then releases 4, so then we'll have 4.
Yeah, so if it gets 2 more, like you said, so why doesn't it release the 4?
It does that.
So if it releases 4 plus what we have left.
Well, we gave it to P1, right? P2. P2. We gave it to P2, right? So when we give those P2 to P2, then we won't have anything available. Then it will release 4. Either you have to decrement the available and then increment the whole, or you just, keep it there and just add whatever that is held right now. It's basically kind of moving a number from this side of the equation to the other, right? Did I answer your question or not yet? No? So you see, we have 2 available. Let's forget about this here. We have 2 available right now, right? If we give this 2 to P2, then we don't have anything available for, some time. And then when P2 finishes, it releases all 4, and then we have 4 available. This is one way to count. The other way to count is I just kind of skip this, intermediate time, and I say at this point I have 2, and at this point P2 is holding 2. Maybe it doesn't request the whole 2 or whatever, I don't care. I have 2 at the moment, and then P2 is holding 2. When P2 finishes, it releases this 2 that it is holding, and then I will have 4. Alright? So, now, let's take a look at resource allocation graph. Last session we talked about this. We had we showed processes with the circles, and then the resources with the squares and the instances inside them. And then there was a request edge when a process is requesting or waiting for a resource. And then there is assignment edge when a resource is assigned after an allocation, right? And then this was an example, right? So, now, today we're going to add a bit to the resource allocation graph, and that is a claim edge. A claim edge is basically before a request edge. So if we have a claim edge from process I to resource J shown with a dashed line, that doesn't mean that the process is requesting right now. It means it may request it in future. We already know, a priori this information. In the deadlock avoidance, processes are declaring. And that's how we indicate them with the claim edge. Now, the claim edge may convert to a request edge instead of a dashed line to a solid line once the actual request happens. And then it will turn to an assignment edge when the allocation happens. Once the process is finished, it releases, right? It releases that resource. So it will turn back to the dashed line, to the claim edge. Right? Because while a process is not finished, it may request and release. So we are never sure. As long as the process is there, we should think of a chance that it may request it in the future. So if a new allocation results in a cycle in a graph, including the dashed lines, then it's an unsafe state, right? And then we cannot allow that allocation to happen. Again, remember, we're adding something to the resource allocation graph, and that is the dashed lines, which is possible requests in the future. Possible requests in the future may actually turn into actual requests. The possibility of the deadlock, we learned last session, was a circular weight in the resource allocation graph, right? Now, right now, if you're safe, that's fine. But if with including the dashed lines, we have a circular weight, then we should not allow that allocation happen, right? So let's take a look at this. So we have an example here. We have resource 1, resource 2. This, by the way, is only working for single instance resource types, right? So we have R1, P2 as requested, R1 is waiting on it, and it has declared that it may require R2. That's why it's in dash line. Also P1 has granted R1, that's an assignment edge, and again P1 has declared that it may require R2. Now what happens if P2 requests R2? If P2 requests R2, what should happen? Should the system give it or not? Why not? A deadlock, it's not necessarily deadlock because it's actually using the dashed lines. It's a possibility. It's an unsafe state. Why? So if P2 requests R2, then this becomes a solid line, right? So fine. Now, if the system allocates R2 to P2, then it will actually turn from a request to an assignment, like this. Now, if this is granted, we have a circular weight, including this dashed line. Right now, it is not a deadlock or something, but it may happen. So we will be in an unsafe state. So this allocation should not happen. The system can detect it and see this and then don't allocate. If P1 requests R2, how about that? Should it be granted or not? Is there any problem? If P1 requests R2, then it will become a solid line. The system can, basically imagine. If I allocate R2 to P1, then the arrow would be like this, and then, well, there's no circle. There's no circular, cycle in graph. So it's fine. We are still safe. So then the system can allocate that. All right? But not P2. All right? So now the banker's algorithm. The banker's algorithm is actually used a little bit more general because it is used also in the multiple resource instances. And each processes have declared their maximum number of resources they may use. And when a process requests a resource, it may have to wait for if this leads to an unsafe state. Basically, that's what we have spoken, but more official, more formal in mathematics. When a process gets all its resources, it must return them in a finite amount of time, right? Because we might be holding other processes to progress. Now, this process should finish and return its resources. So, we have the number of processes and we have the number of resource types, right? Now, we have the available vector, which is for the resource types. So if, available J is K, that means we have K instances of resource type J. All right? And then we have the maximum that the processes have declared. The maximum is n by n, M matrix, and that shows process I may request a resource of type J for a maximum instance of K. An allocation matrix is, again, an n by m, which does not reach maximum, but it's like a current state. At current state, the process I is holding K instances of resource type J. All right? And then the need is basically complementary to this. So it's holding so much, so it may need K more instances in the future. These Ks are not, the same case, basically. So it's kind of clear that if process I it may request at maximum, the maximum number of max ij of resource type J, and it is holding already the allocation amount, so it may need maximum minus allocation, right? It has to be a little bit like this because, you have to solve it, using algorithms. But when you see the examples, it's fairly clear. All right? So each process should declare the maximum of each resource type, and then the allocation depends on the current state, and then the need. So the algorithm basically first has a safety algorithm that tells us if there is a safe sequence and we are in a safe state or not, right? How does that work? We have a work and finish, and they are vectors of length m and n respectively. So the work is kind of how many resource types, instances of each resource type we're working with and we have, having available. Again, not available at the moment, but we are imagining, a few steps ahead. And then the finish is, each processes. Are they going to be finished ahead of time? We imagine if they're, if we allocate them, are they going to finish or not? So initially, the work is the available. So we're going to start with what we have available right now, and basically all the processes has not finished yet. All right. So we imagine. We look for one of the processes that they have not finished, and what they need is less than what we have. If a process need is less than what we have, it means that we can grant them and then they can finish. Again, remember what the sequence was. We can pick one of the processes that we have the resources available. We can grant them, let them finish, and then they release, right? And then we can go over to the next. So this is like the formal. So we find a process that is not finished and their needs is less than what we have, and once we find it, we let it finish, and that's then whatever that they have right now will be added to the currently available resources. And then they will turn to finished, and then we go back to the next process, finding another process. Now we have more available resources. Now we go and find another one, and another one, and another one. In the end, if all the processes are finished, we have, found an order basically that finally all of them can be finished, then the state of the system is safe, and we have a safe sequence. If not, then we are unsafe. So this is the safety algorithm. This algorithm requires an order of m by n squared operation, so it's pretty expensive. But I don't know. So so this is an algorithm that shows, okay, at this point we are in a safe state. Now, what happens if a process PI requests a resource? Now, the system should have an algorithm that can we allow this, can we allocate this or not? Does that leave us in the safest state or not? So, the request I may be the request vector for PI. So the PI now may request 2 of this resource, 3 of that one, 4 of that one, right? It's a vector. So if, again, request I of j is k, that means process I wants k instances of resource type j. Now, if that request is less than the need, go to the next step. If not, that means whatever that they have declared, they are not, they're exceeding their limits. So that's basically an error, and then we should terminate it. If they declare that I want 10 and now they have 5, that means that they at most may need 5. Now, if they make a request of 7, that's just like you terminate that process. Now, if the request is less than available, it's possible, right? Then we can go to the next step. Otherwise, if we don't have the available resources anyways, they have to wait. That's for sure. But if the request is less than available, still, it's not guaranteed. We still, should be a little bit more conservative. So, pretend to allocate requested resources to PI by modifying the state as this. So, the available will be less, exactly by the request. The allocation of that process will be increased by the request, and their need also is decremented. Again, we assume that we have allocated. Now, we run the previous algorithm again. Are we still in safe state or not? If we will be in the safe state, that means this request does not take us from the safe state to an unsafe state, and then we can allocate that to PI. If the next, if we allocate it and then we end up in an unsafe state, then we don't give that resource to PI and then make it wait. All right. Again, this is expensive in terms of computation, but this is the algorithm. Any question? Yeah.
So if you're doing some sort of like prevention, could you not really do priority then?
Could I not do what?
Could you not like implement priority if you have to do this algorithm?
Priority?
Yeah.
Priority does not have anything to here yet. When we're going to talk about like how a priority, for example, can be considered when the processes are against each other. But here we're basically that can be considered, for example, in terms of a preemption. Yes. But when we don't want to preempt resources, then we should not allow more than what we have, right? All right. So this is another example. We have like five processes again, 10 and 5 and 7. Let's see. So currently the state is like this. The 7 instances of A is given. That's why we have 3 available. B, 2 of the instances are given. Again, we have 5, so we have 3 available. And then C, we have 7 instances. 5 of them are allocated, so 2 of them are available. This is the current state. And the maximum that each process has declared is in this matrix, right? So first thing first, we build the need matrix. The need is maximum minus allocation, right? So if it may request 7, 5, 3 total, and right now it has 0, 1, 0, that means that it may need 7, 4, 3 in the future, right? And so on. So you build this, the first thing. Now, are we in the safe state or not? Let's see. So we have 3, 3, 2. Can we allocate it to this? Yes. This can basically finish. So P2, once it finishes, it releases 2 more A's. Now we have like 5, 3, 2. With 5, 3, 2, this can basically start and run, and then it will release these resources. Now we will have 7, 4, and 3. With 7, 4, and 3, this can run, and this can run, and basically all of them can run after that, because the resources will get just released and more, right? So once we're past that point, we can like basically find this, the sequence that works, right? Again, this may not be unique. Don't worry about it. So now when P2 requests 1, 0, 2, so at this point, what should happen? First, we should check if this 102 is less than the available. So it's requesting 102, and we have 332. So far so good. The request is valid. But what happens if we allocate it? We assume that the allocation happens. So if it requires 102, then the allocation will be 302, and our available will become 2, 3, 0, right? And then the same goes with the need, because now it has allocated so much, the need also goes down. So this is going to be what the state will be in T1 if we allocate it. Is this still safe or not? Let's see. Any question? Okay. So is this still safe or not? 2, 3, 0. We still can allow this to finish. So then it will release 3 and 2 of this, and then we'll have like 5, 3, 2. With 5, 3, 2, this can be satisfied, so then it will finish. So now we have like 5, 3, 4. With 5, 3, 4, this can be satisfied, so this will run, this will release. So now we'll have like 7, 4, and 3 or 4, and basically so on and so forth. So this can be granted, and it will be safe, right? And executing algorithm again shows that sequence this satisfies another safety, so it's fine, and we can allocate it. Now these are a couple of other examples. Can request for 330 by P5 be granted in this example? No, for example, because we have available 332. If they request 330, if after this the P5 asks for 330, we cannot grant it because we don't have it. If P1 requests for 020 after this, we have them available. But if you actually assume that you allocate that, then you will realize that actually that leaves us from it takes it to an unsafe state. That's an exercise. All right. Any question on avoidance? We'll go to detection and recovery. All right. So detection has similarities to avoidance in terms of understanding the safest state, but it's a little bit different, right? So how deadlock detection works is that you don't actually do anything, you don't prevent it, you just let the system work and allow the request. But once every now and often, the system basically looks for a circular weight and then finds if there is a deadlock. And if there is a deadlock, then it makes a decision, okay, now what to do, right? Because remember, the banker's algorithm, it's very conservative. Just because a process has, declared that I may require these many resources, doesn't mean that they require it, altogether. Doesn't mean that they may, So we're just like, being too conservative, not allocating resources so that we don't end up in an unsafe state. Not a deadlock, unsafe state. So, we just let everyone just work, and then if there's a deadlock, then we can, figure it out later. So, for single instance resources, the wait for graph actually is easy to draw and then handle. So, for single instance resources, what we start from the resource allocation graph, and then basically we kind of remove the resources, and then we'll find if processes are waiting for processes, right? That's kind of the example that we went over last session. And if P1 is waiting for Pj, it's just like, shows that process should finish. So, remember again, if R1 is a single instance, and it is held by P2, then it means that it only can be released by P2. So if P1 is waiting for R1, it basically is waiting for P2. So that's why you basically start with the resource allocation graph and then, draw the wait for graph. So again, if R3 is is held by P5, that means only P5 can release R3. And if P2 is waiting for R3, that again means that P2 is indirectly waiting for P5. Right? Is it clear? Processes are waiting for processes because all the resources are single instance and they're held by some processes. So now if you turn your resource allocation graph to a wait for graph, it is very easy to find a circular wait. If P1 is waiting for P2 and P2 is waiting for P3 and P3 is waiting for P4 and P4 is waiting for P1, that means that's a deadlock. That's just like the detection. Easy. Right? So in this instance, we have P2, P1, 2, 3, and 4, and a deadlock state. Now, system basically periodically invokes the same algorithm and searches for a cycle in a graph that's like in an order of like n squared. And again, if there is a deadlock, then it goes towards the recovery. And but this is only working for a single instance resources. So the next one, which is useful for several instance resources, again, is similar to what we talked about in the banker's algorithm, but a little bit different. So the available matrix and allocation is the same. Sorry, this is a vector, and then allocation is a matrix. That's the same. Request is different. So the request is the current request of each process. So, if request ij is k, that means the process I is requesting k more instances of resource j. Remember, here we're not dealing with avoidance, so that's why we're not dealing with any maximum or any, a priori information. Right now, this is the state. And this process is requesting these many resources, and we have these many available. Right? So again, kind of similar algorithm. We start with work and finish, and then again we find an I such that this, and this, and this, and this, so on and so forth. If finish is false for some of the processes, then system is in deadlock. It works the other way. So it's kind of like the safety algorithm, but instead of like ensuring that all the processes can finish, it just like wants to detect if some of the processes basically cannot finish. And that means a deadlock, right? If we can, the request cannot be satisfied, in any order, even after all the other processes have finished, we are left with some processes that are just like, still waiting, then, we are in a deadlock. And at the end, all those processes that end up in this situation, they are in the deadlock. Alright? So let's take a look. This again works the same. So this is an example similar to that. So we have like 5 processes, 3 resources, and instances of 7, 2, and 6. So this is the allocation right now. 5 of them is 7 of them, sorry, is allocated, and then B 2 is allocated, C 6 is allocated. That's why we don't have anything available, right? Now, this is the request matrix right now. Now, this process is requesting these many, and so on. Now, the sequence P1, 3, 4, 2, 5 is actually ensuring that all can finish. Let's take a look. So we start with 0, 0, 0, and then when on a piece of paper, you will basically on the work you start writing down and then finishing. So on the work you start with the available, then you kind of like write a note or something. Okay, grant P1, and then P1 finishes. Then your work resources will increase by whatever that is allocated by them. And then you say, okay, now I can grant P3, and then P3 will be finished, and then your work will basically keep increasing and increasing. Right? That's how you should do it on a piece of paper. Right now P1 can start because it does not request anything, so it can finish and release the B, and then also P3 it will release 3 and 3, so we'll have 3, 1, 3, and then P4 is only requesting 1 of resource A, so it can be granted. So we had 3, 1, 3. This will be granted, and then it will basically release more resources, 2, 1, 1. That will make it 5, 2, and 4. 5, 2, and 4 is basically more than all of them, so it doesn't matter, like the sequence you can come up. So it's a safe. Now, if P3 requests an additional instance of type C, right, from this, it will request 1 more of this. Now what will happen? What is the state of the system right now? So if P3 does this, our available is 0, 0, 0, so let's see. We can let P1 finish because it's not requesting anything. Once P1 finishes, it will release 1B. So our work will be 0, 1, 0. Okay. With that 0, 1, 0, can we allow any of these requests? No. So all the other processes that are waiting or making these requests will be in a deadlock. So P1 will finish it, but P2, P3, P4, and P5 all will be waiting because they're requesting some resources that are not available and none of them are releasing them, so they will be in the deadlock, right? So, in the avoidance, basically, we would foresee this and then not allow this to happen. In the detection algorithm, we allow it because we have it, so far. And then now, when this request, then we figure out, damn, we did something bad here. So then is the deadlock recovery. Let's see what happens here. So when we have a deadlock, what can we do about it? So we can either terminate the processes or preempt the resources held by them. Okay? So the termination of the processes is that, okay, when we have a deadlock of some processes, one way is to terminate all of them and just, start them all over or, at a different time, which is expensive. Or we can abort one process at a time and hoping that the deadlock will be, over. So if 4 processes are in a deadlock, if we terminate one of the processes, basically we're forcing that, all those resources are released, and then maybe the other processes now can continue without the deadlock. If not, another process, right? So here, now we have to, again, redetect if the deadlock occurs again. And also we have to be aware how to make the decision, which process we should terminate first, right? What is the, again, criteria? Here comes, for example, a priority. He mentioned this now. Okay? So priority is something that here may show up. So we can start killing processes that are lower priority. And, or how long the process has computed. Right? And how much longer to complete. If a process, is just started and requested a couple of resources, already, well, we can kill it and restart it without losing a lot of computation. And whereas if a process has from a long time and it's very close to finish, maybe we should finish that. Or if a process depending on how many resources that they have held, because if a process is holding too many resources, if we kill that, we release a lot of resources, which then allows all the other processes to finish. Or the resources that it needs. Right now we are in a deadlock, and this process will require a lot of, more and much more resources. Well, if we don't kill this, then it will probably cause more deadlocks again, right? So, killing it might make sense. These are all policy decisions that a system should make, and we don't have to, build systems, fortunately. So, what else? Now, the preemption of the resources is the other way. Either we should force close the processes or just preempt the resources. Which, by the way, I think we talked about it last session. When we force preempt resources from a process, we are messing, with their functionality. If a process is holding a lock or on a file or a disk, they're working on it. If we just preempt the resource from them, that may leave some, corrupted data. Or if they are using some, printer, and in the middle of the printing, if we preempt them from that printer, we have to, make sure that printer is now in a, we restart it so that the state of the printer is now usable. So these are all the, things that when you preempt the resources, you have to think of. Now also, when you want to preempt, again, you have to preempt resources from processes. The same kind of questions you can ask. What process should I pick and preempt resources? How many resources should I preempt? Now, what is the cost of it, right? Because when you preempt a resource, you probably have to roll back that process, a few steps. Because if this process started here, acquired a disk, and did something, now if you want to preempt them, you don't want to terminate the whole process, but you have to bring it, a few steps back so it can start, this part over. How to do that? And how to prevent starvation? What if we, keep selecting the same process and preempt every time? For whatever reason of that, our, cost and policy, maybe we decide this process is not, functioning very well, and we preempt resources from this, and then again let the other processes. And again there is a deadlock. Again we pick the same process. Again we pick the same process. So basically we are starving this process and not allowing this to finish at all, right? So this actually might happen because there are some reasons. If this process, wants too many resources, well, it wants too many resources, so that doesn't change. So if then that brings us to a deadlock every time, we will preempt the same process. So in order to avoid starvation, for example, one way is to include the number of rollback in the cost function. That's something like the aging in the CPU scheduling that we did, right? So that at some point we decide, okay, we should not preempt this process. Instead, we should preempt a couple of other processes and let this one finish, right? So, but we don't have to learn any specific algorithm, for preemption or termination. So for next session, continue working on your PA1, implement it, make sure you make commits, and catch up with the course material because we're gonna do a review session. We have still a couple of minutes. Don't rush out. Make sure stay, and I'm going to be here answering questions regarding to this session because I'm going to make sure that you understand this sessions completely. If you have any questions, go ahead.